In this video, I'll be talking about relative velocities in two dimensions, and then we'll solve practice problems. At the end of this video, you'll be able to solve other practice problems concerning relative velocity in two dimensions. It might be wise for you to check my videos where I talk about relative velocity in one dimension. Okay, in that video, I described this formula. Suppose that we have two cars, car A and car B, where their common frame of reference is the ground. So we had something of this nature: relative velocity of A to the ground plus the relative velocity of the ground to car B. Now suppose that we have more, and the ground in this formula, the ground is the frame of reference, the common frame of reference. Suppose that we have more than one common frame of reference. Let's say it's raining, then we have another frame of reference, let's say R. So the relative velocity of car A to B will be equal to the relative velocity of A to the ground plus the relative velocity of the ground to the rain plus the relative velocity of the rain to car B. So the same thing applies, it goes this way. These are the common frame of reference. And then suppose that you can do it with more than two frame of references. You can do it with three if you have three frame of reference. This actually looks like A to G, and then from G to R, and then from R to B. So that's what it looks like. So the same thing if we have more than two frame of reference. Let's say we have GR and then we have wind. So we'll have something of this nature: AB, then VA, that's AG plus V GR plus VR, the rain, then the cloud C. Okay, wind, we are considering wind, so not C then. So we'll have the wind that we are considering plus the relative velocity of the wind to car B. So it looks like A to G, then from G to R, then from R to W, and then from W to B. So still the same. You can try this with more than three frame of reference. Now let's solve this practice problem. Don't forget that in that video I also told you that this formula is the same as if I have something of this nature, VA minus VB, and then I explained the implication of the two formulas. Now let's solve this practice problem. A boat is heading due north as it crosses a wide river with a velocity of 10 km per hour to the water. The river has a uniform velocity of 5 km per hour due east. Determine the velocity of the boat with respect to an observer on the river bank. Now let's say we have the river as this. Let's say this is the river, and then the boat a boat is heading due north. The boat moves due north with this velocity, and that velocity is relative to that of the water. So we have the boat here. So this is the velocity of the boat relative to the water, and that's equals to 10 km per hour. Now I need you to know that even if it's not stated that that velocity is relative to that of water, it should be noted that this velocity is the velocity that the boat uses inside the water. This is the velocity the boat uses to cross the water. So of course the river will affect it. So that's of course the relative velocity of the boat to the water. Now the river itself has a uniform velocity of this. So the river moves at 5 km per hour due east. So let's say this is the river. The river moves at this velocity, which is 5 km per hour due east. And this velocity is the relative velocity of the river to the riverbank or the seashore. I think in this question we should go with riverbank. What symbol? Okay, let's use B for riverbank. No, we can't use B. Let's use S for riverbank. Now, uh, in some questions you may have seashore, and in this question we have riverbank. These are just terms used. These are common velocities. I mean, these are common frame of references around a river. In other questions we use ground, or sometimes we use earth. So these are common frame of references. Now in this question it was not stated that this velocity is relative to the seashore or is relative to the riverbank, but you should know that whenever, for instance, I told you in that video, in my video on relative velocity in one dimension, that suppose a car moves at p velocity or p meter per second. P meter per second is the relative velocity of that car to the ground or to the earth. So if you were given that a car moves at p meter per second, full stop, it means that p meter per second is the relative velocity of that car to the ground or to the earth. Now in this case, we were given a river has a uniform velocity of 5 km per hour due east. So the 5 km per hour is the relative velocity of that river to the seashore or to the river bank. So, and that's why we have VRS to be equal to 5 km per hour. Now, the question says determine the velocity of the boat with respect to an observer on the river bank. Now, let's say this is the river bank. And of course, this will be the river bank because it is relative to the river bank. Now, let's say an observer stands here. If a boat moves towards the north in this direction, if a boat moves towards the north in this direction, and then a river moves like this, moves the boat in this, of course, it will affect it. And then there is an observer standing here. If you were the observer, what would you see? What would you see? Let me know in the comment section. What you would see is that you will see the boat moving towards you in this direction, because as the boat moves towards the north, the river also moves the boat towards the east, kind of. So this is the east and this is the north, so it affects the boat, and as a result the observer sees it in this direction. That means the velocity of the boat will be towards this direction. So we can label this as, since it is called the velocity of the boat, that means we can say the velocity of the boat relative to the river bank, where the river bank we use the symbol S for river bank. So now, since it forms a right angle triangle, we can go ahead then use the Pythagorean theorem in order to get this formula. But before we do that, I would like to explain the concept. Now, since we have something of this nature, then we can say that the VBS is equal to the VBW plus the V. Okay, I used water and then I used river. I just need to pick one. So I think we should use water. Okay, let's use water and then R for river. So water, river, and then boats and river bank. So R is the river bank, and then W is water, and then the B is the boat. So we can say that the VBR is equal to the relative velocity of boat to water plus the relative velocity of the water to the river bank. Okay, now if we were considering relative velocity in one dimension, you would say that the VBW, which is 10, you can just add this. Don't be tempted to do this, which is 15. This will be very, very wrong, because this is two dimension. In two dimension, we don't just add, we consider the diagram. In this case, we have a right angle triangle, but then don't forget that this equation is a vector equation. And as a result, before we find VBR, we will need to write the vector equation so that we will have something of this nature. VBR, we'll consider the x-axis of VBR, and that will be equal to, I'll still follow this formula, that will be equal to VBW, then at the x-axis, plus VWR at the x-axis. The same, I will consider the y-axis of VBR at the y-axis, then VBW, I'll consider it at the y-axis, plus VWR, I'll consider it at the y-axis, and then the VBR, which is what we're looking for, will be equal to the VBRX squared plus VBRY then squared. VBRX is the horizontal component of the relative velocity of the boat relative to the river, while VBRY is the vertical component of the relative velocity of the boat to the river. Now let's find VBRX and let's find VBRY. Therefore, the VBRX will be equal to VBWX. Now, where is VBW? VBW is only on the y-axis, and that's 10 kilometer. It has no component on the x-axis. What I mean by it has no component on the x-axis is that the VBW is just along the north. VBW is along the north. It's not something like this. If it were to be something like this, then we can say it has something on the y-axis and then it has something on the x-axis. So it's only along the y-axis. So the VBRX, that will be 0 plus, I'm using this formula, so VBWX will be 0. Then then VWRX, the VWR, this is VWR, the relative velocity of the water to the river bank, which is this. On the x-axis, the x means on the x-axis. On the x-axis, it is 5, and it's plus 5. It's not in the opposite direction, so it is 5. We can say that this is 5, and then VBRY. Now, the VBRY is equal to VBWY. Then VBWY is along the y-axis, and that's 10 plus VWRY. VWRY has nothing to do with the y-axis, so it's just 0 because it lies on the x-axis completely. So we have 10. So it implies that the VBR, which is the square root of VBR squared plus VBRY squared, so we'll have 5 squared plus 10 squared, which as a result will be 11.2 meters per second. So that implies that A is the answer. Now we can actually find the direction. We can find the direction. The direction will be theta. Okay, before I explain that, let me just cut this off. Now it should be noted that the x that we got here, which is 5, we got it as 5, so we can say this is 5 and then this is 10, something of this nature. They are both positive, so we can say that no, so we can have angle theta here, and then this angle is the same thing as this angle, so I can have it as 10. So that means the theta is the arctangent of y, which is 10 upon 2. So that implies that the arctan of 5, the arctan of 5, that's supposed to be equal to, that's supposed to be equal to 78.69, 78.69 degrees. So that means theta is 78.69, and this angle is the angle from the x-axis, is the angle from the x-axis. So we can say that theta, the direction, the direction of VBR, the direction of the boat relative to the river bank, is 78.69 degrees north of east. So, or we can say it in the other way around. We can use this place in the other way around by saying 90 minus 78.69, 19 minus that, that's equal to 11.3. So we have 11.3, and in this case this direction is from the north, so we can say that the relative velocity of the boat to the river is 11.3 degrees east of north. East of north, off shows where the direction is coming from, so it's actually coming from the north and it's taking 11.3 degrees. Let's say we do not have a right angle triangle. What do we do? A cyclist traveling southeast along a road at 15 km per hour feels a wind blowing from the southwest. To a stationary observer, what are the speed and direction of the wind? Now, a cyclist traveling southeast, this is southeast, so this is the southeast. So this is the relative velocity of the cyclist, cyclist C, to the ground. Okay, now the cyclist feels a wind. The wind blows 25 kilometers southwest. This is the southwest. The wind blows towards this direction, so the wind should probably be coming from this direction, and then so we can say that the wind goes this way. It's actually from the southwest, so it goes this way. The wind is actually popping up like this, so we can just represent it's a vector. We can also put it here, it's the same, they are parallel to each other. So let's erase these ones. All right, so this is the velocity of the wind relative to the cyclist. and that's equal to 25 kilometer per hour. The velocity of the cyclist relative to the ground, that's 15 kilometer per hour. So we can say that the question says what are the speed and direction of the wind, and then I told you that whenever you are asked speed of the wind without any frame of reference, that means it is the speed of the wind relative to the ground or any other common frame of reference. So since we are considering the ground as our common frame of reference, so we need to use it here as well. So the formula, the equation, the vector equation will be velocity of the wind to the ground, then wind to the ground, plus velocity of the ground to the no wind to the cyclist, and then the cyclist to the ground. All right, in my video where I talk about relative velocity in one dimension, I already explained this formula. Now, to find the relative velocity of the wind relative to the ground, which is VWG, I told you this is a vector equation, and in two dimensions we need to resolve. So we can say that VWG with respect to x, so that will be equal to WCX plus VCGX, and then the same thing for y-axis, y plus VWC, no, equal to plus VCGY as well. Now then what we are looking for, VWG will be equal to the root of this and this, which is VW is as simple as that, squared plus VWGY and squared. So we get to have something of this nature. Now let's find this VWGX, which is supposed to be equal to VWCX. Now the VWC is the relative velocity of the wind to the cyclist at the x-axis. Now this is the relative velocity of the wind to the cyclist. Let's check it at the x-axis. At the x-axis, that means I will need to resolve this to the x-axis so that it will become VWCX at this place. If I resolve it to the y-axis, it will become VWCY. Now the wind blows at southwest, so it's actually at the middle. So this is 45 degrees. As a result, VCX will be equal to, and is at the positive x-axis, VCX will be 25 cos 45 degrees, and then VCY, that will be equal to 25 sine 45. I already explained this in my video where I talked about resolution of vectors. Relative velocity of the cyclist to the ground, if I resolve it to the x-axis, that will be VCGX, which will be equal to 15 cos 45. If this is 15 cos 45, then in this place that will be VCGY, that will be minus 15 sine 45. It is minus because it's along the negative y-axis, and then I've already chosen sine. Since we already resolved, the relative velocity of the water to the ground at the x-axis, at the x component, is equal to the relative velocity of the water, then the cyclist at the x component, and that's VWCX, which is 25, which is 25 cos 45. So in this place we'll have 25 cos 45 plus then VCGX. The VCGX is 15 cos 45, so we have 15 cos 45. So if you do this correctly, that's 15 cos 45 plus 25 cos 45, then you should arrive at 28.28 28.2843. Then we can also find VWGY. The VWGY, that's the relative velocity of the water to the cyclist at the y component. So we can have this, which is 25 sine 45, then plus VCGY, which is this, which is equal to minus 15 sine 45, and that's supposed to be equal to 7.071. As a result, the VWG, relative velocity of the wind to the ground, is the square root of this. Now, let me just explain it this way. What we have simply done, the VWGX is something of this nature. This is the VWGX. Because we could not just find the resultant, it's not a right angle, and that's why we need to resolve. So it becomes something like this. So this is the VWGY. So, and this is the resultant, which is the VWG. So we can find the direction. The direction is this angle, angle theta. That's the direction. So as a result, since we already have it as a right angle triangle now, it's the same thing as we can use the Pythagorean theorem, which is the same thing as the formula I gave, which is this, the same thing as this, the square root of VWGX squared, and that's equal to 28.2843 squared plus, okay, plus 7.071 squared. So if you do this correctly as the magnitude, then we should have something of this nature. Let's see. That's the square root of 28.2843 squared, okay, plus 7.071 squared. So we'll have 29.15. So that's equal to 29.15 kilometer per hour. So you just need to understand your diagram. Then be able to resolve. It's as simple as that. Then this is the formula. You follow your formula, and then you should be able to bring out the components from the formula. It's as simple as that. So to find the direction, this is the direction, the arrow. To find the direction, we'll make use of the tan. Since we have the y-axis and the x-axis, the y-axis is VWGY and the x-axis is VWGX. So we can make use of tan theta as a result of SOHCAHTOA. So SOHCAHTOA, the TOA of SO is the TOA of the SOHCAHTOA is tan, which is equal to opposite upon the adjacent, and the opposite in this case is VWGY. The adjacent is VWGX. The VWGY is 7.071 upon the adjacent, which is 28.2843. So we can say that the theta is the arctan of 7.071 upon 28.2843. So we can say the arctan of that. So if you do that correctly, you should arrive at 14 14 degrees. And that means the angle we drill something like this. We drill something of this nature, and we called this as VWG. It means that the angle which is from the east to that VWG, we got it as 14 degrees. So it means that from the east, it means that from the east, if it is from the east, then you say of east. From the east to the north, it is 14 degrees. Or you can say it in the other way around. You can, by doing from this side. If you want to get it from this side, then you need to do 90 minus 14, which is equal to, which is 76. And then you can say that, and this is actually from the north. That means it is 76 degrees east of north. That means from the north, 76 degrees to the east. So that's the direction. That's the direction.